Right, so welcome to this webinar. I'm Ryan Mewis. I'm based at the Manchester Metropolitan University. I'm going to be talking to you about embedding Benchtop NMR in the undergraduate curriculum. So I'm just going to detail briefly the motivations for why we want to do this. And principally it's to diversify the range of NMR instrumentation provision that we offer our students. So this means, as well as offering high field instrumentation, we also offer benchtop NMR provision as well. The next key point was really to give students basically as many opportunities of experiential learning of NMR, which is relevant to their course as possible, because this allows them to actually put the theoretical underpinning that they're actually being taught and will be learning in their lectures into practical practice. And that's really quite important to actually make those two things linked together. We also wanted it to map onto our hands-on approach that we want our lab classes to have. And what I mean by that is that all the instrumentation is freely available for our students to use, so they can actually go and use it whilst they're actually part of a lab practical class. So if they're making something in a synthetic lab, they can immediately go and actually ascertain and elucidate its chemical structure as part of the actual lab that they're involved in. And lastly, we wanted to increase the student exposure to NMR by increasing the representative amount of experiments that utilise NMR. So this is just not just organic, but also inorganic examples as well. Right, so the instrumentation used for this piece of work, we have a Oxford Instruments Pulsar Benchtop NMR, which is located on our teaching floor. So the students have easy access to this instrumentation, and we only purchased that back in 2016, so it's a relatively new acquisition, and we've been working on ways of actually implementing this into our undergraduate teaching program. The data that comes off this instrument we process using Mnova, and we produced a series of user guides for how to collect the NMR data in the first instance and its subsequent processing by Mnova in the latter stage of the actual experiment. So in terms of what we started to do to actually implement NMR into our undergraduate curriculum, primarily we only have one second-year undergraduate laboratory practical at the minute, but as you'll see later on in this talk, there are many more in development. We also allow our third and fourth year students to use them during their project allocations, so they have basically unrestricted access again to use the instrumentation. And we've also rolled this out to our FDSC course, which is a foundation degree in science. This is a long distance learning course, and the students typically come into the university for what's known as like a residential week, where they do a portfolio of experiments and also gain access to a load of instrumentation that they don't use in their jobs currently. And NMR is one of those things that we've implemented there. So principally this talk is going to look at a series of practical experiments that use the NMR benchtop in conjunction with actually processing that by Mnova. First one is the NMR coursework assignment. Then I'm going to talk to you about the reduction of 3-nitrobenzaldehyde to 3-nitrobenzyl alcohol. I'm going to look at the synthesis of dimidone, analysis of some transition metal ACAT complexes, and the synthesis of ferrocene and its subsequent acetylation. So that's a mix of organic and inorganic types of practical. So I'm going to start off by taking you through the NMR coursework, and like I say, this is for a second year cohort, so students that are in their second year of their degree, and we asked them to elucidate the structures of two unknown materials, which are basically listed as A and B in the scheme that we've got below. And those two compounds, they come together using sodium ethoxide to make this compound here. And if we want to give some relevance as to why we're actually looking at this compound, it forms this part of this structure over here, which has got very potent anti-HIV activity. So this is quite nice for the students who are doing pharmaceutical chemistry to see the relevance of actually why they're doing the organic chemistry. So we provide them with the CHN, infrared and mass spectrometry data, and also the carbon NMR. But we actually task the students with actually collecting the proton NMR data for compounds A and B. And this is both the collection of 1D and 2D data, such as COSY. They'll bring all this together to actually elucidate their structures, and then they use a mechanism to actually work out how this product here is formed. And this utilizes inorganic chemistry, micro additions, all the types of things that an undergraduate student at this level will be learning, so they can actually put this into practice. I've just got a small note there at the bottom of the screen that this actual experiment has actually been written up as a laboratory practical, and it's currently under review in the Journal of Chemistry Education. So I'm just going to take you through what compound A looks like in terms of basically the students going out and collecting the NMR data side of things. So for those of you who are familiar with Benchtop NMR and actually its provision of actually looking at organic molecules, we'll recognise this as being ethyl crotonate. It's almost like a gold standard that's used universally, irrespective of the provider of the actual instrumentation. It's really nice because it separates out really well in the proton NMR domain, and you get really good resolution. From a teaching's perspective, it's got some really good key components. First of all, we've got this ethyl group, which is between where protons A and B are located. And this is because the students will have actually learned about ethanol, which has also got an ethyl group, so we can actually use that as a natural extension into something that's slightly larger. It also has this alkenic moiety, where we actually have we could actually get cis and trans isomerism that exists, and this is something that they will not be able to actually elucidate using infrared or mass spectrometry. And this is where the power of NMR comes into being, where you can actually use the coupling data that's actually embedded in the multiplet structures to actually deduce and actually work that out. So that's something that we're trying to encourage the students here to do, is not just actually work out a structure, but really actually define definitively what type of isomerism it may actually possess. So as we can see from this example, the multiplets resolve very nicely. We've got good integral data that we can use, and they can actually effectively label the peaks that are present in the multiplets to get the chemical shifts, and from that they can actually get the J coupling. So as well as collecting this 1D spectrum, we also like them to collect the 2D proton-proton COSY, and this is another nice way of actually putting the theory that they are learning into practice. So they actually learn about 2D NMR, other experiments such as COSY, HMBC, and they can actually then use that to further help them elucidate what the actual structure of this molecule is. And the students really like this because effectively it is like joining up the dots, and that's something they find that they can actually get to grips with rather readily, such as the fact that A and B shows a COSY-like interaction, and whereas D, C and E all show COSY interactions. And by doing so, they can actually start to break down that molecule into two small subsets, which allows them to actually tackle the problem easier, from an easier perspective, because they only have to deal with two components rather than the molecule as a whole. And that for some students is really quite nice, because it doesn't actually overwhelm them in trying to actually deduce the structure all at once, and they can do it in parts as they so wish. The note there on the side, it says that it took about 30 minutes to collect this, and the great thing about ethyl crotonate is it's got really good solubility, so you can really make the samples very concentrated. As well as the proton NMR data, we supply the students with carbon NMR data. The reason why we don't get the students to collect this for themselves is because it just takes an inordinate amount of time, and we like the students to actually be a bit more proactive and actually basically doing other experiments and actually collecting as much data as they can, whereas the carbon is simply just a very repetitive experiment that takes a long period of time to collect. Equally, this spectrum was collected on the same instrument, just to show that you can actually get this type of carbon spectrum. And so again, we can provide this to the students, and they can use it to identify the number of carbon environments in there, but also the actual environment in which they exist, as denoted by the difference in the chemical shift environments. On top of this, we also provide them with the depth spectra, and from this they can actually start evaluating those carbon environments to an even greater degree, particularly in the fact that we no longer see the quaternary in the spectrum, which has no depth signal, and the fact we now have a phase difference due to the difference of either having CH or CH3s, which are in absorption or positive mode, compared to this only lone CH2, which is actually in the emission mode. And this is also very helpful because on top of the information that we get, for example, for peak B, is the fact that it's actually got a chemical shift there of 60.55 ppm. So the students can infer about the actual local environment, in particular the fact it's bonded directly to oxygen, which is perturbing that chemical shift and makes it considerably different to pK, to which it's coupled to. So it's all these little snippets of information that they're going to start bringing together to actually elucidate this structure. And it's important to actually put across really that the students are provided with a numerous of tutorials before they do this. We are building up their skills to elucidate these types of structures and actually go through and show them the actual methodology basically of how to start breaking the structure down and then how to actually put those components back together to give the total structure. The second compound that the students are tasked at looking at is ethyl acetyl acetate. So this is compound B. It's a much simpler compound. We've only got 4 proton environments now, and so there's also some overlap here that we can see with ethyl crotonate in the fact we still have this ethyl group which involves proton environments A and B. So they can actually use this to try and get some kind of comparison between the structures. There's a similarity that exists there, and then they can actually use the rest of the actual information to deduce what is different about the structure, which is this component over here. You'll notice on this proton NMR spectrum there are 3 signals that are indicated with an asterisk. These all belong to the enol form of this ethyl acetyl acetate. It tautomerizes in solution, and again this is something that a second year undergraduate chemist will be learning about keto-enol tautomerism. In this case the equilibrium is doing very much towards the keto form rather than the enol form. A lot of the students actually do pick this out, which is very pleasing to see how they pick this out and actually pinpoint it actually being down to the keto-enol formation tautomerism that takes place. And again, that's demonstrating the fact we can use NMR to give them insight into the theory that they're learning during their lectures, and they can actually see that in the data that they've collected. So another example of a organic experiment, something that we may be looking at actually getting the students to collect the proton NMR spectrum of is dimidone. And dimidone is another molecule that exists in the keto and enol forms in solution. And again, the use of Benchtop NMR allows all the 6 different environments that exist in the 2 tautomers to be separated out, which can then be integrated to give an effective percentage of how much exists in one form and how much exists in the other form. Again, the dimidone's got relatively good solubility, so you can acquire this spectrum in less than 1 minute. This is a spectrum that students actually collected for themselves. We can tell that because we've got a peak at about 4.75 ppm, which doesn't relate to actually either compound or tautomer A or either tautomer that's present. So again, the students can actually use this. They can actually have a think about why they're actually seeing 2 subsets of peaks, and maybe they can also think about the presence of the enol form, why they don't actually get any kind of difference between this proton environment here and the protons over here as well. And that's because you've got basically very, very rapid exchange of this proton here over to the actual ketone and back and forth on the NMR timescale. So we're actually seeing only one basically averaged position over the actual 2 different varieties or 2 different forms that we can actually see for that. So again, this is another example of some keto-enol tautomerism. Fits on very nicely with the undergraduate chemistry that they are learning, and then they can actually put that into practice in a laboratory environment. Moving on to another type of experiment, which is the reduction of free nitrobenzaldehyde. Very simple spectrum to start off with, in the fact we've got this benzaldehyde at the aldehyde group, about 10.14 ppm, and then we've got all the aromatic protons together, and basically they're very overlapping. So we're not using this experiment here to actually look at chemical structure, although we do actually see the aldehyde group reduced into the methyl alcohol group, which we'll see on the next slide. We're using this to actually get the students to predict what the appearance or the effect of going from an electron withdrawing group, which is the aldehyde group, to that of the methyl alcohol group. And you can do this using Euler's rules, so you can actually look up the tabulated values for the electron withdrawing group and electron donating groups, and actually forward predict what the actual spectrum of the product looks like in terms of the aromatic region. So if I just move on by one slide, we can now see the results of doing the reduction, which is easily achieved using sodium borohydride. We can see that we've got two new peaks in the form of the actual CH2 at 4.81 ppm, and also the OH, which is going to be concentration dependent, but here we see it at 2.41 ppm. And again, for the aromatic region, we have quite an overlap in terms of the actual protein environments that are present in the aromatic ring. So we can't really break that down and actually work out very easily which protein environment they may actually belong to. However, we get the students to actually think about using Euler's rules, where we can actually look at the substituent constants for the NO2, the aldehyde, and the methyl alcohol group. We can then actually predict some chemical shifts for each of those protein environments that exist in those two different materials. Principally, if we go from the reactant to the product, we see that the actual shifts are going upfield. We're seeing a much smaller chemical shift in terms of the actual aromatic protons present. So, although the actual spectra quite clearly identifies that the aldehyde has been reduced, but it can also get them to think about the effects of the electron withdrawing and electron donating groups on the electron density that's actually in the aromatic ring, and how that affects the chemical shifts that we see in the proton NMR spectrum. So in the next slide, we've got the two different materials, the product shown there in lilac and the reactant shown in dark blue. And we can see, particularly in the aromatic region, how there's been a shift upfield in terms of the product relative to the reactant. So this is, again, we're trying to get to actually predict what the NMR spectrum looks like. So we're actually getting the students to actually hypothesize and then evaluate their hypothesis when they actually collect the NMR data. And then they can actually validate if their hypothesis is right. So rather than actually collect all the data and then have to interpret it, we're trying to get the students to actually think about what they're going to expect at the end. So I've just got a few inorganic examples. These are basically revolving around two new labs that we're hoping to put into practice for this forthcoming academic year. So we haven't actually been able to really test these out yet on a cohort. So we've got an example of where we're looking at some paramagnetic and also diamagnetic centers borne out by the different metals that are used in each case. So the first experiment, we're looking at a different series of transition metal acetyl acetate complexes, one of which is this manganese complex. And we're mainly using magnetic susceptibility measurements to actually calculate the number of unpaired electrons to gain insight into whether the metal is operating in a high spin or low spin configuration. The manganese experiment is quite a nice one because it's D4, so it can either be high spin or low spin, but in both cases they're both going to be paramagnetic due to the actual unpaired electrons. So the actual NMR spectrum doesn't quite clearly identify whether it's high spin or low spin, because in both cases they're going to be paramagnetic. However, what it does do is actually highlight to the students that we're not defined by the fact we have to focus all of our attentions on the 0 to possibly 12 ppm range of the proton domain. Here we've got an example that goes from 0 ppm all the way up to 30 ppm. And principally we're not trying to use this spectrum to actually get the students to elucidate where the methyl groups or the CH of the ACAC ligand are, but to show them actually what the effect of a paramagnetic center is on the actual proton NMR, and to actually get them to actually think about why that is, and actually get them to go away and read up about what happens when you've got a paramagnetic center and how it affects the actual NMR spectrum. So again, we're trying to use this to actually basically create something within the student to actually have a hunger for basically wanting to try and find out why they've got this spectrum and why it doesn't actually fit into the normal domain that they expect. So again, this goes a little bit beyond what we'd actually want to utilize in this respect. The Ferrocene example is one that we're just basically rolling out again this year. Ferrocene is a classical organometallic complex. It's got 2 cyclopentadiene rings, forms this lovely sandwich complex. And you can see that the proton environments of these 2 cyclopentadiene rings are all equivalent, as we only see a single peak in the proton NMR spectrum. Okay, so you can ask the certain questions here about the Ferrocene structure, because initially it was only thought to actually go through one of the actual double bonds in terms of bonding to the ions. So you can actually ask that question about how they can actually deduce the type of bonding that's present in that Ferrocene molecule based on the actual proton NMR spectrum. We can then acetylate the Ferrocene ring or Ferrocene ligand or complex, and when we do that we get a completely different spectrum. Again, this is where we've actually added the acetyl group onto this cyclopentadiene ring up here, but this one remains untouched. And we can now see that in the proton NMR spectrum we've got a greater number of actual proton environments that are being generated. Again, the protons down in this environment appear as a single environment, so they give rise to only one peak. We have one peak for the protons involved in the acetyl group, but then the protons of the top cyclopentyl ring are split because of the actual proximity to the acetyl group. So we've got those protons that are located on these positions here and also here, and then you've got the beta sets which are located on those 2 positions over here. And another great thing that we can see in the spectrum is the fact that the 2 triplets for the alpha CH and the beta CH show second order effects or roofing in terms they actually are leaning towards each other due to the actual very small difference in terms of the chemical shift relative to their actual J coupling. It's worth pointing out as well that the J coupling here within these 2 triplets is very, very small. It's about 1.5 Hertz. But even on the actual benchtop NMR, we can effectively resolve that out, and so the students can actually get some information from that and try and work out what gives rise to those 2 triplets. So that kind of covers the range of different experiments that we've either actually implemented or in the process of implemented here. I just want to give you some student responses that basically relate to the coursework experiment to try and highlight why the students are actually benefiting from actually having access to NMR and actually undergoing this experiential learning of NMR as part of their course. So we've got one student here that said they learn better by actually doing the practical side of chemistry rather than just theoretically doing stuff. Okay, that's a very student-like comment there, but it is very true in the fact that NMR can be quite a dry subject, but actually having the actual ability to go out and do it allows you to actually bring that theory out and apply it in the practical sense. Another student said that doing a practical as part of the coursework was good and gave them a better understanding, and that was pleasing to see. The next student, one of the students said it was a lot more fun to understand a new process. Now, from a pedagogic side of things, whenever someone says that it's fun to learn, that's always great to see, because generally if you enjoy what you're doing and you're learning whilst you're doing it, you're obviously going to keep with it and engage more and more. So that's a really positive comment there as well. And lastly, this was another really good comment to see, that one student thought that knowledge of NMR is really useful for future job prospects. So they're actually thinking beyond their degree and actually thinking that having access and doing these practical experiments was actually going to help them get a job at the end of it. And that really maps on really well to basically our hands-on approach here. So just to summarise what I've been talking to you about today, been showing you a range of different NMR experiments that are suitable for the undergraduate laboratory, and they are inorganic and organic based, so you've got a range there to look at. So I think a lot of people tend to think of NMR as being mainly organic centred, and as an inorganic chemist I always like to challenge that. The students collected and processed their data using SpinFlow and Mnova respectively, and what we actually saw was the students like to peer support one another through that process, in the fact that maybe one student had already done it and they'd actually sit with the next group and help them through. So that was really nice to actually see that kind of embedded in the course there, in terms of actually peer support for a new process, and the fact they're actually getting something out of it as well. They're actually able to transfer that knowledge onto other students around them. The students were positive on the inclusion of NMR to help link theory to practice, and that they might be useful for future job prospects. And we've also been able to use this for our foundation degree in science students. They've benefited considerably from the actual opportunity to collect their own NMR data, and they've been using that to enhance their portfolios, which they use to get accredited for that course. So where are we going next? Well, I'll talk to you a little bit about the transition metal ACAT complexes, and they use the magnetic susceptibility balances, but we're thinking of basically expand this to actually using the Evans method, so we can have a look between a solid state and a liquid state sample. And this maps on really well to the fact that one of our members of staff here likes to do a lot of these Evans-based methods, which tends to always use the high field instrument, where the student doesn't really get that much of a look in. But if we can actually do that on the benchtop, then the student can really take ownership for that and actually take that forward. In terms of some student outputs, there's been a small technical note that's been published by David Ashworth and Lisa Clayton with myself last year. At the time, the students were actually in their second year of their degree, but they were able to actually use both the SpinFlow and Mnova package to actually basically calculate some T1 data, for basically my area of research, which looks at hyperpolarization. So just like to finish up today by giving some acknowledgements to the people who I work with here, Dr. Oliver Sutcliffe, Vittoria Caprio, Paul Burkett and Stuart Langley. They've really been instrumental in actually rolling out these experiments and getting the actual benchtop NMR in the first place. And they're actually being very enthusiastic in terms of actually suggesting new experiments that we could actually do to embed NMR even more into our courses. I'd like to thank David Williamson and Andy McLachlan from Oxford Instruments for their help and assistance, and also for basically acquiring the carbon NMR data that I presented today on their instrument down in Oxford. I'd like to thank Enrique for all his help in actually getting this webinar up and going today, for all the support over the last few weeks, and to Dr. Manuel Perez for basically inviting me to come and do this in the first place. So that's basically the end of my webinar. I'd like to invite you basically to put some questions up, and I'll be very happy to answer those based on what I've presented today.